Okay, so today we're looking at kinetic energy and velocity of molecules. And we're going to start off by saying that molecules are always in motion. Scientists refer to this as kinetic molecular theory. Molecules are always in motion, and what determines how fast they're moving is their temperature. So here we have a sample of gas. We're going to go with the big blue ones here. And here are our molecules at a temperature of 300 kelvins. And they're moving around our chamber. It's a sealed chamber, so they can't get out. And they're bouncing off the walls, and they're moving. Some of them are moving a little slower. This guy's kind of slow. See him? This guy's moving pretty quick. See him? Ooh, that guy's flying. Look at him go. Wow, bang, bow. And we're taking their average velocities. Notice that if we were to inject a sample of our smaller molecules, whoa, those guys are flying. Holy mackerel. Notice that they're all at the same temperature. If we were going to calculate their kinetic energy using the formula from physics for kinetic energy is equal to 1/2 mv squared, where m is mass and v is velocity, the bigger molecules don't have to go as fast to have the same kinetic energy as the smaller ones. So what we're going to say is that the kinetic energy of molecules is the same regardless of their mass, as long as they're at the same temperature. So for us to calculate the kinetic energy on average of a sample of molecules, it's a real simple equation. We're going to say kinetic energy average, and this is going to be for a mole's worth of molecules, is going to be 3/2. We're going to multiply that by R and temperature. This value R, we recognize this value because 8.314 joules over Kelvin moles. And of course, this is going to be our temp in kelvins. It's a real simple equation. We're going to modify it slightly so that we can also calculate the kinetic energy, average kinetic energy for individual molecules or atoms. And it's a real simple equation. We're simply going to replace R with what we're going to call the Boltzmann constant. And it's a constant like anything else, 1.380649 times 10 to the negative 23rd joules per Kelvin. So if we're going to ask the kinetic energy for a sample, we could do it for individual molecules, or we could do it for a mole of molecules. Let's try at least one of these and see if we can make this work. Okay, let's try these two problems here, where we've got a sample of krypton gas, and it's giving us the atomic mass units, the mass and atomic mass units. We don't really need this for now, okay? So let's try this out. Let's calculate its average kinetic energy at 130 kelvins, and we're going to start it off by calculating the average kinetic energy per mole, and you'll see how it works in the units. So our equation is going to look like this: 3/2 times our gas constant R times our temperature in kelvins. Well, if we're going to crank this out, our gas constant R is 8.314 joules over moles Kelvin, and our temperature is 130 kelvins. When we do this, kelvins cancels kelvins, and it will leave our answer in joules per mole, which is what we want. So let's crank this out. I'm going to scoot this over, and let's bust out our calculator. And we're going to say, let me turn this on. We're going to say 3/2. I'm going to put that in decimal form, 1.5. And we'll say 1.5, same as 3/2, times 8.314. And then we'll multiply this by the temperature in kelvins, 130 kelvins. Here is our kinetic energy in joules per mole, 1621.23 joules per mole. We'll come back to that moles part in a little bit because we're going to answer the second part using Boltzmann's constant, but we're going to see that you can get that same answer if we take joules per mole and convert it to molecules. So let's try this one. Our kinetic energy average, in this case per atom or molecule, since it works the same way, we're going to use this equation, 3/2 over times Boltzmann's constant times our temperature T. Well, Boltzmann's constant is right here, 1.380649 times 10 to the negative 23rd joules per Kelvin. And we're going to multiply this by our temperature, 130 kelvins. And when you do this, kelvins cancel and just leaves your answer in joules, because that's it, how many joules per atom. So let's bust out our calculator here, and we're going to say 3/2, otherwise known as 1.5. We're going to multiply this by 1.380649 times 10 to the negative 23rd, and we'll multiply this by our temperature in kelvins, 130. Here is our energy in joules per atom or joules per molecule. We'll round that. We'll say 2.7 times 10 to the negative 21. This is going to be joules per molecule or joules per atom. Would we get the same answer if we tried to convert this from joules per mole to joules per molecule? We can easily find out by converting this. Because we have moles on the bottom, we'll put moles on the top, and we'll divide this by 6.02 times 10 to the 23rd molecule. Do we get the same answer as we get using Boltzmann's constant? Let's say 1621.23, and we'll multiply this by 1 mole, which is not necessary, and divide this by 6.02 times 10 to the negative, times 10 to the 23rd. Do we get the same answer? Ta-da! 2.7 times 10 to the negative 21. So you can get this answer in joules per molecule by either dividing your answer in average kinetic energy per mole by number of atoms in a mole, or you can use Boltzmann's constant and you get the exact same answer. All right, let's go back to this simulation and let's look at what's going on with velocity. So in this simulation, we can see that all of our gas molecules are at the same temperature. Right here, we see it up here at the top, 300 kelvins. And yet, look at how fast the red ones are going. I can't even keep track of some of these. The blue ones I can follow pretty good. I mean, that guy, well, he's kind of slow. But look at this guy, this red one. The difference is that the red ones are smaller. And so for the exact same temperature, smaller molecules are always going to be moving faster than larger ones because their kinetic energies are the same. If we go back to our equation for calculating kinetic energy based on mass and velocity, we see that my computer's being slow. Here we go. Let me scroll this over just a tad. Hang on, let me pause while my computer is catching up to me. Apologize for the glitch. What this is telling us is that for the same kinetic energy, one molecule that has a smaller mass will compensate by having a larger velocity, and molecules with a larger mass will compensate by having a smaller velocity. We're going to plug this into an equation to calculate root mean square velocity. Let me show you how this works. So now we're going to look at how mass and velocity are related, and this equation is pretty close. We're going to say that we know that the lighter molecules for the same temperature move faster and the larger molecules for the same temperature move slower. the equation that we're going to use is going to look a lot like that, but it's going to look slightly different. We're going to call this root mean square velocity. That's the U, and it's a real simple equation. Root mean square velocity of a particular molecule works like this: 3RT over m, and we're going to take the square root of this whole thing. And so here's how this works. We're going to use 3, obviously. This R is going to be our gas constant, 8.314 joules over moles Kelvin. This temperature is going to be temperature in kelvins. This one is the one we want to be careful about. We're going to call this mass, but it's got to be in kilograms, and we'll see why in a little bit. All right, so let's try one. So let's ask, what is the root mean square velocity for water vapor at 300 degrees Celsius? Let's remember that water is H2O, and it has a molar mass of 18 grams. We're going to get that into kilograms for our equation, so we're going to divide it by 1,000. We get 0.018 grams. Let's plug this in. What's our root mean square velocity? The equation we're going to use looks like this: 3RT over m, which is mass in kilograms. So let's plug everything in. We're going to say 3, and we're going to multiply 8.314 joules over Kelvin moles, and this is telling us at 300 degrees Celsius. So let's get that into kelvins by adding 273, and we're going to divide this by the mass, which we know in kilograms is 0.018 kilograms. Now let's focus on this joules. If you take a physics class, you might find that you calculate joules is equal to force times distance, which is newtons times meters. That's a joule. And you get your newtons by multiplying your mass in kilograms by the acceleration due to Earth's gravity. And that means that a newton is another way of saying a kilogram times a meter squared over second squared. That's why we want to get our mass in kilograms, so that when we do this, our kilograms cancels, our kelvins cancels. Remember that our molar mass is kilograms per mole, so that will cancel out our moles as well. It's going to leave our answer in meters squared over second squared, which we're going to eliminate when we take the square root. So let's do this, and we'll say, what is the root mean square velocity of this sample of water at 300 degrees Celsius? So we'll simply say, let's get this where we can read it. We're going to say 3 times 8.314 times 573. We'll take this answer, we'll divide it by 0.018, and then we're going to take this answer and we'll plug it into our equation for square root. So we'll take the square root of this answer, and here is our velocity, 891.06 meters per second. Now, if that's a water molecule, we expect, the velocity to be pretty big. But let's try that if we did it with something smaller, like hydrogen, which we know has a mass of 2 grams, otherwise known as 0.002 kilograms. We would expect this velocity to be quite a lot bigger. So let's try that over here. So we're going to calculate our velocity of our hydrogen at the same temperature, and we're going to say root mean square velocity is going to be equal to the square root of 8.314 joules over moles Kelvin. And remember that a joule is another way of saying a kilogram times a meter squared per second squared. And our temperature is still 300 degrees Celsius, otherwise known as 573 kelvins. Our mass is quite a bit less, 0.002 kilograms. So let's plug this into our calculator. And we're going to say, let's make sure we can see what we're doing here. We're going to say 3 times 8.314 times 573. Crank this out. We'll divide this by our mass, which is 0.002 kilograms. and then we're going to tell the calculator to take the square root of this answer. Wow, quite a lot faster, 2,673.2. 2,673.2 meters per second. At the same temperature, our water molecule is moving a lot slower. And that's all we're doing. So I'll see you guys on the next one.